Close enough to start, so we'll go ahead and get started. Um, we are now sitting in week 3, so all this week 1 stuff should have been done. All this week 2 should have been done. In week 2, there are a couple things I want to point out. Topic chosen. I don't remember who. Somebody sent me an email saying that the link for the writing assignment directions weren't valid, and that's because they weren't. For whatever reason, that page never copies across when I copy Canvas courses. It is now fixed and it should be visible, so you should be able to see that. And then I sent an announcement, or I sent a directed email about paper homework number 1 sometime Sunday. The vast majority of the class got that and responded. There's about 4 or 5 of you that are missing that assignment. So if you're missing that I would argue is effectively free points. You should be going through and getting that done because it will soften the damage of the exams. Speaking of exams, we've got week 3, which is this week, and then week 4 is our exam. So our exam is actually going to hit us next Wednesday. So please be preparing and thinking about that. That said, we do have some pretty rough stuff, I would argue, to go through within this week. We've got Lewis structure, and we've got kind of the conclusion, if you will, of quantum theory dealing with electron configurations. We kind of back away from the electron configurations a little bit because students look at them and get a little bit crazy within them, and I don't blame you. But since it's Chem 130, we don't look at them quite to the level of detail that you might be thinking we do. Your first real active homework is due whatever the 8th is. That might be Sunday. So you should be working on that. And yeah, office hours were really exciting this morning. I had all of nobody show up. Okay, so I get it. Doesn't have to be you. OChem could show up too. Has anybody been trying to come in to office hours online to see me? Because quite frankly, I'm nervous about that linkage actually working. Okay, just checking. Because I did actually set it up today. So what I've got is things that I would highlight to talk about would be isotope weight and averages, electron configurations, and I personally like Lewis structure a lot, and so I would even get started into Lewis structure, which is a bit of a challenge considering the vast majority of you have not watched the Lewis structure, at least we video, because it hasn't been due yet. Like it's due, I think, tomorrow. So you probably don't want me to get into Lewis structure. How do we feel about isotope weights and averages? Was that you should ask questions? Oh, you're actually going to ask legitimate questions. Even better. Scroll. You actually got it? You ready? Okay. Oh, the one thing I didn't open. The gallium example from the practice exam? Cool. Okay. Clean. Let's do clean. So before we get into the gallium example, just like with the lecture video, I want to kind of talk through some of the origin behind where this is coming from and why it exists. So I guess prior to this kind of discussion, how would you go through and determine the average of all of those numbers? Okay. So for the sake of the recording, the general consensus, we just add all those numbers into our calculator and we divide by the total number of numbers that are there. Okay. Is this going to be fun to add up? Okay. Should be relatively easy, right? You just keep entering the numbers and kind of go all the way through. But the process of adding up all these numbers would be a bit tedious and a bit obnoxious to kind of have to deal with. If we consider what's happening on the atomic scale, when we're looking at isotope masses, okay, and their averages, we aren't looking at whatever numbers that is, 15 numbers. Okay? We're looking on the scale of tens of thousands, if not millions, if not billions of numbers. And so sitting there and just entering that number plus number next, number next, number next, billions of times is going to take a lifetime. Okay, so we want some way to simplify this approach and kind of reorganize it. So how could we do this without having to add every single number up? Any ideas? No ideas? That's fine. I'm just checking. Taking an educated guess would be a little bit dangerous, but you can make the argument that yes, you could try and pull off an educated guess. And I don't know why I can't pick different colors, but we're just going to work with what I got then. We could go through and start to note that there are repetitions. Oh, because it's not doing what it's supposed to. What happened? Gonna work now? There it goes. So we could go through and see the number 1 shows up a bunch of times. So we could say 1 shows up 3 times, right? So if we were going to do the math on that, right, it would just be 1 times 3. Make sense? Do we notice anything else? Okay, multiple 3s. I already skipped one. 1, 2, 3, 4, 5, 6. So we have the number 3 times 6 times. Plus what? Cool. Doing it for me so I don't have to do it all out. 2 is up there. Whoops. If we try and maintain consistent patterning behind this. The number 2 is up there, you said 3 times? What else do we have? I'm out of colors, but 4 is up there how many times? I can't pick up that same pattern, can I? 4, so almost do it again, is up there once, and 5 is up there once. Okay, that would shorten some of our work. And if we talk about this on the billions scale, that would narrow it down a little bit. Okay, so that's really just changing the addition part of it, and then we would divide that all by the total number, right? Does that make sense? Okay, I said 15. How many was it? It was 14? I literally just picked a number and picked 15. 1, 2, 3, 4. It's 14. That would have been amazing. Okay, so that simplifies it a little bit, but then the next thing we could do would be simplify it even further. We could start to separate out all those pluses into their own individual calculation, okay, which at first seems a little bit silly, but we're going to go through and do it anyway, because silly things sometimes are not that bad. So 1 times 3 over 14. I'm not going to color code anymore because this is annoying for me. 3 times 6 over 14. Plus 2 times 3 over 14, plus, come on, there it goes, 4 times 1 over 14 plus 5 times 1 over 14. Yeah? Okay. And for those people frantically writing, you're more than welcome to take notes if you want, but I would argue this is just kind of the thought process to getting to where we want to be. Okay? So why is that beneficial to me? Okay, and you may have no clue. I don't understand why that's beneficial at all. Okay, well, the number 1 shows up 3 out of 14 times. Okay, that's going to be a percentage, right? 3 out of 14. And if we do percent, what is percent? Per 100. So how would I get it to 100? 3 divided by 14 times 100, and we're there. Okay, and that could give us a percentage value. So why does this help us? Well, this can take us then to a generic form. We can reference the number that we're monitoring times its percentage. And we can take the number for the next one times its percentage, and the number for the next one times its percentage, so on and so forth. Kind of, sort of. So this is going to change things a little bit. So if I have the ability to determine what the number is and the percent of the sample, I can now rerun my average to this system or to this kind of formula. Okay? And this is going to give me an average, but in the process of doing this average, like I did all the way at the very beginning, it's still an average, but this average is reformatted. Is reformatted in a way that we would typically call it a weighted average. Ultimately, you're doing nothing different mathematically. All you're doing is rearranging that information to get it into a configuration that allows you to input different sets of data. So instead of running what some would call a simple average, you just add everything up and divide by the total number, we can kind of reconfigure that to then say, well, what are the numbers I'm trying to average? What's the percent that that thing shows up? And I can do it for every single one of those numbers I'm trying to look at an average for. Kind of makes sense? This ultimately does a couple things for us. Number one, it helps you understand grades, because most grades run through a weighted average. Right? Particularly for this class, if you go through and look at just raw points, it's not a point-based class, it's percent. The exams are worth 50% of your grade. The other sections are worth 10%. Okay? Why do we do that? Because it's simpler for me mathematically to deal with. I can just dump assignments in, and I don't have to worry about their point value totaling out to make sure that everything scales right. Okay? Why else would I do that? Well, if I have an exam worth 100 points and an assignment worth 10 points, you look at that 10-point assignment and you go, well, that's worth a tenth of the exam. That's a pretty big value add behind it, so I'm going to do that. But if we actually look at the weighting associated with it, the contribution to your grade, that 10-point assignment is probably worth less than 1% of your grade, whereas the exam is worth 10 to 13%. But the human brain doesn't deal with those percentages really well, and instead of really drilling in to look at the nuances behind it, we just look at the absolute values of those numbers. Faculty do tricks like this all the time. They'll give you a homework assignment that's worth 100 points. You go, an exam is 100 points. Oh my God, this homework must be worth tons and tons of points. But then when you look at the percent contribution to your overall grade, very, very different. So we can play with your perception of those numbers to make you do the assignment. Okay, so that's how we can use it just within the class, okay, from an education realm. Does this mean you could now go through and manipulate all of your grades and be like, is this really worth it to me? Yes, you absolutely can. Okay, but I would argue for all those small assignments that individually don't contribute much, what they do contribute is effectively free points that in the grand scheme mean you can not do well on exams and still pass the class. Okay, so I've done all that work. Have all your other instructors? I don't know. Okay, I'll leave that to them to figure out, or you to figure out and then take advantage of their grading system. But I didn't say that. Might be recorded. Kind of, sort of. How do we use it content-wise in the class? Because content-wise in the class, it's a different story, okay, or a different manipulation. And this goes back to the question of how we would ask it. So how we would ask it is in the practice exam. Okay, or one way we would ask it is in the practice exam. Of course, that's a little too... I don't have the ability to delete text off. I sort of do. So make sure I undo this. Okay. So we now have gallium that has two isotopes. Okay? We're told the mass and we're told the abundance for one of them. And we now want to know the mass for gallium for one of those isotopes to 4 significant digits. So do you need to stress about significant digits in this question? Okay? We might say yes, because it says it. But I would argue, no, you don't have to stress about it because it says it. If it's going to tell you you report to 4 sig figs, you report 4 sig figs. You don't have to think about it as hard. It's not an implied undercurrent, which a lot of our calculations will always have an implied undercurrent. Here, you're actually explicitly told what the sig figs are. Okay? So what was that formula that we summarized on the other side? Okay? The number times its percent. Well, what's the number that we're going to be looking at here? Totally understand how you're answering that. You're giving me an actual number. I don't want the actual number. I want the thing that you're monitoring. What about gallium? I want its mass. So when we're talking about using this formula, particularly for our isotopes, and we'll double back to what isotopes mean in a second, we're talking about the mass of one isotope, okay? And I can say, I want to put a label in here. Should I say the mass of gallium-69? That's fair. I personally don't like that because that's going to introduce another number into my calculation that may confuse me as I navigate this. So what I might go through and do is call gallium-69A. Okay, so I want the mass of particle A. And what's my formula? Times the percent. The percent of what? Percent of is a lovely statement. Okay, the total mass is not going to be a percent. That's everything. Yes, what did I just? Yes, what isotope? I'll accept 2 answers, gallium-69 or A. Okay, so for me, I would again specify A. Okay, plus the mass of B. Okay, because again, I don't want to incorporate more numbers if I don't have to. Come on, show me a parentheses. Okay, so which one is B? Gallium-71 is going to be. Okay, times. Okay, I'm going to go with the percentage of B. I totally understand why you want to say X. We'll come back to that in a second. The percentage of B. When I add those all up, what do I get?
The average mass.
This is now the average mass. Okay. Why do I not want to put in X yet? I want to make sure I've got the formula that I'm going to work with down, written down, and not worried about. There's very few things that you absolutely have to memorize here. I would argue this formula is not something you have to memorize. But what you have to do is be able to manipulate simple averages to weighted averages. Are you comfortable with that? That's a personal question. Some are like, yeah, I totally get that. Great, that's fantastic for you. Other people may not be confident with that, and so what should you do instead? Memorize this. Okay? Memorize this formula so that when you see an isotope question, you can manipulate it. Okay? I don't want to put in X yet because I don't necessarily, me personally, know what I'm solving for yet. Okay? You're brilliant, you figured it out. Good for you. Okay? So now I want to go back to the question and start pulling out the information the question gives me so I can start dealing with a plug-in chug. So does the question give me the mass of A? Okay, what is the mass of A? How do you know that's the mass of A and not the mass of B? Okay, some people will laugh at this. Okay, this is something that you have to be careful with. You have to read the question and based off the structure of the question, answer whether it's A or B. That can be a challenge. That's one of the things that you have to practice. This is why I would recommend looking at practice questions to get a feel for it. Just the context, we haven't mentioned any other species at this point, gallium-69 with a mass. The sentence is saying that mass corresponds to A. Why did you shift, you horse? Come on, No, other way. Thank you for the support back there. That was A. What is the percent? For A. Okay, so what I would do is potentially circle. If I'm on a testing situation, I would go through and say the mass of A was equal to 60, that's a 6, 68.926 AMUs. What is AMUs?
Atomic mass units.
Atomic mass units is a perfectly acceptable answer. More generically, what is it? It's our unit. When do you need to include a unit? Always. Okay, so what's the unit on 60.11? Yeah, it's a weird one. It's a percent. What does percent mean? Part of 100. Percent is 100. So we can mathematically switch this around to call this 100. That's 60.11 what? I've already done percent. Somebody else mumbled it. I heard it. 60.11 what? We already did percent. What's the 100? The 100 is the whole. So what's the 60.11? Which part? It's the part that's A. Okay. This is our whole. Okay, if we're going to continue through, I need what else? What other information needs to show up? I need the mass of B. Does it tell me the mass of B? No. And in fact, what does it ask for? This is where we look at the question, what is the mass of B? That's actually what I'm solving for. So this is where I would go through and put in my X. Okay, what else do I need? The percent of B. Does it tell me, for those of you that are doing weird mental gymnastics, don't answer. Does it tell you the percent of B? No, it doesn't. Okay. Last thing we got to worry about. It's the last thing in the formula. I also need to know the average mass. Okay. So if we're looking this setup of all these pieces, we've got some dilemmas here. Okay, we for sure know what we're being asked to solve for. We've clearly identified that as X, but I don't know what the percent of B is, and I don't know what the average mass is, which then means I effectively have three unknowns in one equation. If we go back to our algebra, that ultimately means there's a ton of, an infinite possible solves for this. Okay, only one of those infinite possible solves is correct. So you have to be able to narrow it down to one of those infinite possible solves. To do so, the only unknown needs to be the mass of B. Percent of B and average mass have to be determined so that I can solve for the mass of B. So the question becomes, how can I solve for those?
If you scroll up, you can get the mass of gallium by itself on the periodic table, and it's A69.72.
Okay, we'll pull it off of this periodic table because I don't want to deal with the shifty things again. When we talk about the average mass is always given to you when you know the element. Where is it always given? It's on the periodic table. That content is implied within this. You are now chemists. You are responsible for knowing that content, which then means the average mass, again, we'll pull the periodic table on this one up here, 69.72. Am I in black? Good. 69.72 what? Cool. That's a step in the right direction. What's the percent of B? What's that? Can we use the percent of A to find the percent of B? Yes. Why and how? What information did this whole question start off with? Gallium has two isotopes. So if I tell you A was 50%, what's B? How did you do that? You did some kind of mathematical operation. Cool.
Solving for the difference out of 100.
Okay. Recognizing that if we're looking at the sample of a total of 100, okay, what color? I'm just going to accept. If we have 100, we know the percent of A plus the percent of B must total to be 100. Why? There's only two isotopes. So if I know A is 60.11, how do I solve for the percent of B? I just run my subtraction. The percent of B is going to be equal to 100 minus 60.11. 39.889.
Oh, what's that? Another one, sorry.
Okay, no, that's fine. I was like, wait a second. Okay, so we can now take that information back over to our system over here. This is 39.88%. This was B over the whole. And what could we now do?
6.89.
Okay, just fun. Everybody's favorite thing, all we gotta do is plug and chug now. Sub the numbers in and run your calculation. Okay, do you want me to show the sub of numbers in? Yes? Okay. So, come on, pen. I'm not going to color code through this though. The percent of A, so we have 68.926 AMUs, or sorry, the mass of A, times the percent of A. I'm going to do 60.11 over 100. Whoop! Why that and not 60%? Well, I can't multiply by 60%. What could you multiply by? 0.6011, which is 60.11 divided by 100. Okay? So it's that decimal value that you can incorporate. It's up to you. Do you trust that you can do that decimal point shift and not screw it up? Yeah, go for it. Otherwise, you should divide it by 100 because that's what it is. It's per 100. That's what percent means. Okay? Plus the mass of B, that's what I was solving for, so I'm going to leave that as my x times the percent of B, 39.89 AMUs over 100. This equals my average, 69.72 AMUs. At this point, those numbers look a little bit big to me, so what I would start to go through and do is solve that first set first. Figure out what that number is. Did somebody do the math?
41.4314.
Jiminy Christmas. 41 point.
431.41.
Okay. Do we need to carry more decimals? Why? It said to report to only 4 figs. So should I have called this just 41.43? No. When you get to your sig figs, you want to round your sig figs at the end of your calculation. Do I need to list off all the other numbers that he gave me? No, as long as I've got a couple extra decimal places, those are more than enough to account for any kind of rounding error, and I'm good to run from there. Okay, plus 39.89 times x equals 69.72. What can I do? Okay, it's not agreeing with me because it's fighting me. Fuck software. You better not have deleted everything. Okay, I can subtract 41.4314 from both sides. I'll get 39.89x. Did somebody actually do that math?
And 28.2886.
86. Okay, now what do I do? Don't round yet. Divide both sides by 39.89. And I get x equals, oh, remember. So I'll have to make sure you don't lose your numbers. We'll multiply both sides as well. What'd you get for your number again? 2. I actually said 70.92. Appreciate that. Did you get that same number?
Yeah.
Okay. Dumb question?
Yeah, sorry.
That wasn't an accusation. Apologize.
I said that. Is there a difference between bringing the 100 down and doing the math in that bottom portion with the 39.89x? Or could you do the math 39.89 divided by 100, turn that into the correct?
You could turn that into
And then do the
0.39
math.
and then do the math. Yeah. Just based off how I'd written the work, I had left that off. So if I was an instructor evaluating my own work, I would point out the fact that I screwed up that division of 100 and maybe I should run that calculation first. Okay? To improve my correctness all the way through this process. Does that make sense? Okay. Does this number make sense? Why does it make sense? What if I'd gotten 68? Would that number have made sense? Why not? Stupid. Way to leverage what you had in front of you. What if it came out as a calculation that I got 68? Does that answer make sense? No. Why not? A was 68.926, so I'm going to say 68 is different than 68.926.
Because if they're both lower than the total average, then the total average should be lower.
Okay. If we have two isotopes, the average is in between those two values. I know one of the values is 68.926. My average is 69.72, which means the missing value has to be larger than the average. I can process of elimination to say that 70.9165 makes sense. Did you guys give each other hiccups now? What if it came out as 72? What if our answer came out as 72?
I'm sorry, why does it make sense?
We'll double back to that. If our answer says 72, we ran the calculation and the number it spits out is 72. Do I have anything that would allow me to say that that was an unreasonable answer?
Yes. Because 69 is not the average. That's no point.
69.72 isn't a middle point between 72 and 68? Were you done with the work? Okay. And some talking made me nervous. We have our A point, we have our B point, and then our average is somewhere in between. Okay, where in between is it? It could be really close to A, it could really be really close to B. And this might be what you're pulling off in your head. A was 68.926. The average was 69.72. What I'm saying is if your calculation said that your answer was 72, do you see anything that screams that that average is impossible? Okay? And everybody's going to see this a little bit differently. I would argue we could absolutely get an average to that value. What would we have to do? You have to change the percent makeup. Okay? So could I get an average of 69.72 with a 72 mass? Absolutely. That value is somewhere in between. Is it going to hit the 60.11%? I'm not good enough to look at 60.11% and be able to manipulate where that's at quickly and easily. So if I hit a 72, I'd be like, I guess. And I'd move on. Does that make sense? Okay. Doubling back to, what if we'd said that answer was 68? If we run our calculation and it says B was 68, could that answer make physical sense? No. The average has to be between those two values. 69.72 is larger than the 68.926, and it's also larger than what we came up with for B. What does that mean? B is wrong. What does that mean? It's a good thing I erased all the mathematics, because what I need to go back and do? I need to start over because I screwed up the calculations. If I got 68, don't be freaking out yet. Okay, if I got the 68, I didn't. What I got was the 70.92. Okay, and if that's that number, yeah, that seems reasonable. Does that make sense? Okay, I've got the answer scratched out, or answer choice is scratched out. Is this a correct answer? Nope, it's not a correct answer because it says 4 sig figs. This doesn't list 4 sig figs. What I would have to do after I've done my calculation and written this down, or do it live as I'm doing this, say this is 70.92, right? Because the 6 is my first insignificant. It's larger than 5, so I need to add 1. Is this a valid answer? We're getting the same mixes of yeses and nos. Good. Number-wise, lovely. It's not a valid answer because it's missing the units. Now you could go through and box that in. What if you left the units off? Then you'd be wrong. True. How many points do you deserve to lose? Okay. So for some of this class, you should be very thankful that I'm your instructor and not some of your classmates that are like, you should just lose everything. I would argue leaving the units off is at most half a point. Okay. Leaving sig figs off on this, again, half a point. So if you come to 70.9165, you're missing the units, you're missing the sig fig. I would argue that's 4 out of 5 points. You did the vast majority of what was asked, and you're missing some very final small touches. So that becomes an interesting question. So if your calculator spits out 70.9165, do you need to write that down? I don't think you need to. You could directly write 70.92. Okay. I don't need to see your significant figure calculation because ultimately, do you really see any work as far as sig fig calculations? I wrote a little bit, but I would bet none of you wrote that. Okay, does that make sense? So yeah, sig figs is not something to show your work. It's I look at the answer, did it match? Yes, good, move on. Okay, which for better or worse could mean that you just luck into it. Does that make sense with the percent? Okay, so what's the deal with isotopes in general? Because this only comes about because we have isotopes. Well, what the heck is an isotope? Okay, so this goes back to our subatomic particles and what our subatomic particles contribute to an overall atom. You have protons, neutrons, and electrons. Okay, the protons contribute to, well, ultimately all of them contribute to everything almost equally. Okay, but once you've defined one, the others start to narrow their field. Protons define the element. If I tell you 2 protons, you can tell me. You should be able to tell me. Helium. Okay, that could be based off the periodic table, which conveniently nobody looked to the periodic table that tells you the answer. You're not looking at it. You're all flipping chemists at this point now. I'm sorry, 2 weeks in, 3 weeks in, you're chemists. You need to use the periodic table. Okay, so if I tell you 2 protons, you should immediately be looking at the periodic table. I don't expect you to have it memorized. I expect you to use it. Okay? So where do I see on the periodic table that it's telling me 2 protons? On this periodic table, it's that top right number. It's our atomic number. Can that atomic number move places? Yes, it absolutely can move places. I'm going to delete all this work. Maybe. Sure. Yes, almost exactly. Okay. If we go through and take a look at this periodic table that's on the exam, is the atomic number in the upper right-hand corner? No, it's not. So it can move around on you. Okay. Where is it typically going to be? That top bar. Okay. I've seen it in the left, I've seen it in the middle, and I've seen it on the right. Okay. But it's usually up at that very top. That's our atomic number. The atomic number is what's defining our element. And what defines our element? The number of protons. So if I tell you 36 protons, you can tell me KR. Nice cop out. I said nice. What is KR? Close enough. Krypton. Okay. And when we talk about close enough, why is that close enough? Where am I going to ask about the names of an element? Is that something that would be show your work? No, it makes absolutely no sense to show your work there. Okay, so you'd see that in the multiple choice. And if you saw krypton and kryptonite, hopefully, I mean, could be wrong, but hopefully you would avoid the kryptonite and go for the krypton instead, even though they both sound Supermanish. Kind of make sense? What happens if you change the number of electrons? And that one gets a little tricky because we haven't really talked about that one. So far, when I tell you that helium has 2 protons, you should be able to tell me that helium has how many electrons? 2. Why?
It's a neutral atom.
We make the assumption that it is neutral, that the protons and electrons equal each other. So once we know it's helium, we know it has 2 electrons because we're assuming neutrality. Okay? Could it be unneutral? Yes. Where would that information be written to allow us to know that we're talking about an unneutral thing, which I know is a stupid way to say it, but that bridge has already been crossed. How do I know that helium would be not neutral? Where's the information about charge stored in my atomic notation? Okay? And if you're looking at the periodic table, that's a neat idea, but the periodic table ain't going to help you. Periodic table doesn't show atomic notation. But I am trying to provide you a hint. Only if you don't turn around and recognize where I'm at, though. What was that? It's on the right side. Fantastic. There's a lot of right side. Where else am I? The top. We're talking about charge. Charge is written in the upper right-hand corner. Okay? That charge is the balance of protons and electrons. But once I've defined that I have 2 protons, the charge is now going to be dictated based off the number of electrons. So if I had a negative helium atom, a negatively charged helium atom, how many electrons do I have?
At least 3.
It's not at least 3, it is exactly 3. Because 2 electrons would completely balance out. I need more negative. What particle is a negative? Electron, so I have to add another electron. Once I've added that other electron, I'm now negatively charged. What happens if I add another electron?
Still negative.
It's still negative, but these are not bunny ears. -2. Okay? I can have as much negative as I want theoretically. Where do I specify the number of protons? Periodic table is fantastic, but we're talking about atomic notation now. Where do I specify the number of protons in atomic notation? The bottom left. This is my atomic number. The atomic number is our number of protons. And you'll note, but the periodic table has it on top. Why is that? Because they wanted to mess with you. I got no explanation. Okay, so there's our protons. Are down. Lovely that it shifted on me. We've got our electrons up here. We talked about isotopes. What was isotopes? More or less neutrons. Okay, where are neutrons? Totally fair answer. Let me try and change the question around. Where's the information about neutrons stored in my atomic notation? It is the mass number, not the atomic mass, and that is located where in my atomic notation? Top left. Okay. I heard a lot of people shout out something about the bottom right, because of course we now have a corner down there. What is specified in the lower right-hand corner? And people are going to be like, I have no idea. What's the formula for water? H what? Where's that 2? It's the amount of atoms in your individual notation. So anytime when we look at H2O, H2O is technically trying to use nuclear notation. They dropped a bunch of information off. Why? Because it wasn't relevant to that formula. Okay? Why do we want the mass number to be the first thing written up there? This went through in the videos, but it went through fast. Okay? As it's presented in the textbook, they call it atomic notation, but they don't talk about charge. Charge are electrons. The only thing they talk about is the mass number and the atomic number. So what they're referencing is actually not atomic notation. They're only talking about the protons and neutrons. And the protons and neutrons are found where?
In the nucleus.
In the nucleus. Okay? Why does that matter? Well, this notation is only telling us about nuclear stuff. Why do I care about nuclear stuff? Or when would I care about it? We just care about it all the time. Actually, no, it's very rare for us to care about it. They do dictate the isotopes, but even then, Why do I care about the mass number? Why is that going to be the first thing I want to see? When do I use nuclear notation? Try it a different way. Who would use nuclear notation? I never use nuclear notation. And I'm a chemist. What chemist would want to use nuclear notation? You mean like nuclear power plants? And why would a chemist working in a nuclear power plant care about the mass number? When that mass number gets big enough, what happens? We now have the potential for explosions. So if we're talking about a nuclear chemist, their primary concern is seeing a mass number that's big enough to cause radiation. If it's big enough, yes, they care. If it's small, they don't care. That's why that number is written there, is because it's written for nuclear chemists. Okay? Why is it almost never written there in any of our other notations? Because we don't care. Okay, so it gets dropped off very quickly. Why is the atomic number dropped off? What did the atomic number specify?
Number of protons.
True. And what did the number of protons tell us?
What the element is.
And if I look at my symbol notation, what's the very center of that symbol notation? The element. So I can drop the atomic number because it's already redundant information because I've written the element. So if we're going to talk about the utility of atomic notation, the only part that's actually relevant would be the parts that the textbook chooses to ignore. Okay? Every other part of it is just a factoid for you to memorize for a test. Do you have to? Yeah. It's part of the expectation. Kind of, sort of? Okay. So now where is this information found on the periodic table? Well, the periodic table really just tells you the atomic number and the atomic weight. It does not tell you the mass number. Because what was the mass number? What was the mass number? The number of protons and neutrons for that symbol. The atomic weight is not the mass number, it's the average. This is why when you look at those atomic weights, they aren't all whole numbers, that you'll see them vary a little bit. And they're varying because of the different isotopes that are possible for that element. That's why you're seeing them change. Periodic table, by definition, is yes, exactly that, the average mass of the element's isotopes. Which is useful because that's how we solved that whole gallium question. We had to use the periodic table information to pull that off.
So would you put for the mass number, would you just put 4?
So how do you determine what that mass number is? Okay, which is I think really what you're asking. So if I tell you we're looking at helium, what's the mass number? 4.000. Okay, let's go to the 0.000. What was mass number? Protons plus neutrons. Is there a decimal point associated with that? No, it's an exact measurement, which means 4.000 doesn't make any sense. So if I ask for the mass number for helium, what's the answer? You don't know. Because if I'm asking for that element, the only way you would know that is if you've studied helium enough to know what its common isotopes are. Does it only have one isotope? If it only has one isotope, then it's going to be 4. Okay. Does it have only one? Maybe. Based off the periodic table we're looking at, it says 4. We look at the periodic table on the screen in our recording, it says 4.003. Do you think it has more than one isotope? Probably, and that's why it's not a whole number. Okay? So how could I get you to tell me the number of neutrons for an individual isotope? I have to tell you the mass number. Okay? So how do I tell you the mass number? I want the number of isotopes the number of neutrons for helium 4. When I write the 4 after it, what does that number specifically refer to? That's the mass number. So if that's the mass number, you could go through and say, well, this is 4 and then helium. Do you know the atomic number? How do you know the atomic number is 2? You find helium on the periodic table, you see its atomic number is 2. How many neutrons are there? 4 minus 2 gets me 2. It's almost like it's lined up to do some mathematics to figure out the number of neutrons. Kind of make sense? No. What if I tell you... Shit, I already forgot. What was your question? Do another example. How many neutrons? I wanted to ask a different question, and I entirely forgot what my question was. So, reformatted. How many neutrons does that have?
17.
How do you do that?
So 32 is the mass, then I know that's the neutrons plus the protons combined. And then I go to phosphorus, and that says it has 15 protons, so I subtracted the 15 from 32 to get 17.
There it is. Make sense? Does that help as an extra example? Slightly different format?
So would it normally be written as like 32P or helium-4?
Both.
Then it means the same thing.
It means the same thing.
Okay.
That's not an eraser.
When
question I wanted.
neutrons and electrons.
Okay, so what if I tell you you have protons being 11? We'll just call that a positive, pretend that's positive. 12 neutrons and 11 electrons. What would the atomic notation be? Don't flip that over and look at your answers. And if you have the practice exam in front of you, don't look at your answers. So if I have 11 protons, 12 neutrons, and 11 electrons, what's my atomic notation going to look like? Cool. Why do you, okay, didn't even get my question out. So we go with protons to find the element. That's quite all right. So 11, so we know it's Na. Since we know that, we also know something else that we could immediately put into our atomic notation. Not the mass. What else can we immediately put into our atomic notation? Where does the 11 belong? That's that lower left. Okay. Now what can you do? Which I think some people were doing as you were shouting out some other numbers. 11 protons plus 12 neutrons is 23, which is the mass. I'd like you to say mass number for the record, just so you're aware, mostly because I screw it up. Okay, where's the mass number written? Top left. Where are the electrons written? Okay, this is an interesting question. They're not written, sort of. Definitely not in the bottom right. The bottom right, remember, is the amount. How many times does that element or that symbol show up? So definitely not the bottom right. Okay, I would argue the electrons are accounted for in our notation, though in this case it becomes kind of a moot point to address them. Where is the information about our electrons stored? Top right. The top right is where our charge is. That's our balance of protons and electrons. What is the balance of protons and electrons? They're the same. There's 11 protons, 11 electrons, which means what's my charge? Neutral or 0. I could go through and write a 0 in that upper right-hand corner, but what I would find is I'd end up writing a lot of zeros. Okay? That gets painful and redundant, so typically what do? I just don't. Okay? And then that satisfies this. So why are the electrons included? Well, now if you flip over and look at all your possible answer choices, you'll see some where we're adding electrons together with our protons to get 22. And if we have 22, maybe we're talking about titanium as the symbol. Okay, so if you don't know what those symbols mean, what those pieces mean, and you just start randomly jamming numbers together, those random iterations of possible things are an answer choice. Okay, who does that trip up? The people that didn't prepare and are trying to rely solely on test-taking strategy. And you're like, but you can't do that. Yeah, I can. Okay, the point is that you show what you know. Okay, so be very careful looking at your answer choices. You run a calculation, you go, oh, that's totally one of the answer choices. That doesn't mean you're right. That just means you potentially ran the calculation in a way that I predicted. Okay? So make sure that you answer the question not because it shows up as an answer choice, but because you know it. And if you're like, but I don't know it, that's okay too. You're fine. Do whatever you got to do without cheating. Okay, to specify your answer and defend it for yourself. That's okay. But if you know the answer, do not look at the answer choices. Because what do you see in the answer choices? You see the wrong answers. And if there's 5 answer choices, you see 4 wrong answers. And believe it or not, if you really poke at my exams, what you'll find is each of those 4 wrong answers follows an inherent common flaw that students make when trying to process things. Which means avoid looking at the answer choices until that's your last straw. Answer the question first, then worry about answer choices.
If there was 12 electrons, would you write a -1 in the right-hand corner?
Cool. If there were 12 electrons, does that change your answer? Well, now if I have 12 electrons, are they perfectly balanced out, protons and electrons? Nope, I have one extra electron. So how do I report that in the upper right-hand corner? It's the balance of charge of the protons and electrons. So really what we're saying, and I tried to zoom in and thankfully it didn't move anywhere, is you've got 12 positive things. I did it again. You have 11 positive things plus 12 negative things, which ends up with one negative thing. So what gets written in the upper right-hand corner? A -1, or sometimes just the negative symbol.
If it was 13 electrons, it would be -2.
We made it 13 electrons. We run the exact same calculation, the exact same process. You just total up those pieces, and then, yeah, you have an excess of 2 electrons. It's now -2.
Could you still write it as just negative even if it's a 2? Or is that just
You can't just write it as negative if it's a 2, because a negative is going to assume a -1. If you wanted it to be a -2, you have to specify it as -2. There's another way to do it that's for really, really old, probably dead people. Let's not worry about that. Specify your number. Slight alteration on this. My chosen notation is magnitude. I may be wrong on this. Magnitude, or sign then magnitude, right? Okay, so sign is positive, negative, and then magnitude 1, 2, 3, 4. Okay, that's my preferred notation because I care about the sign. The sign is what drives all of the chemistry that I worry about. So I want to see the negative first. The standard notation that I've seen textbooks, stop moving. Is to do this. 2 negative. It means the exact same thing. I don't know why that's the standard notation that people use. I think it makes absolutely no sense. The most important thing to note is the charge itself, whether it's positive or negative. The magnitude of that number is a secondary aspect. Both of those notations are equivalent.
Do atoms ever have fewer electrons than protons, giving a positive charge?
Yes. In fact, sodium is one of the prime examples. Sodium is not likely to actually gain electrons. It's actually more likely to lose electrons. Is that something you should know? Yeah, that is something you should know at this point. Why and how?
Because of ionic bonds and covalent bonds.
Okay, so there's a dodge, which is what I'm going to argue you're going to use here, saying, oh, because we have ionic bonds. And because we have ionic bonds, there's this thing where we have to memorize the common ionic charges. Yes, in that respect, that does count as a way to get through this, that sodium should be memorized as a plus 1, not a negative charge. It should always be positive. Okay, that is a hand-wavy way of just saying, I don't want to learn the chemistry, so I'm just going to memorize the fact. Is that valid? Yes, 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 that is perfectly acceptable. I get it. Okay, I don't like it, but that's not on you, that's on me. Okay, so how do we know that sodium should be a positive and not a negative? Okay, what we're talking about is the balance of electrons. Where are there electrons? Do we know where electrons are? Number of protons is now just referencing how many electrons. I didn't ask how many electrons, I asked where the electrons are.
Yes,
Yeah?
on the outside. Yeah.
Cool. Anywhere on the outside? Used a good operative word in there. This would go back to the lecture we used in Thursday, which I know hurt people, but you've had the whole weekend to watch the quantum lecture, and I think another lecture that kept pushing on electrons. Okay, where are our electrons located? In orbitals. which means when I go through and look at sodium with its 11 electrons, I should be able to predict where every single one of those electrons is located, and I should be able to label it. Okay, this is going to get annoying right away because I'm going to show the longhand first for this. What we're talking about is its electron configuration, where all the electrons are in every single space. Okay, and then we'll talk through how we can do, whoa, yeah, don't look at that, go away. I mean this, I don't want the periodic, well, that's as much white space as I can get. Take what I can get. Okay, so if we're going to look at sodium, I need to address 11 electrons, right? Where's the very first electron located? The inner shell. Which inner shell? The first inner shell. How do we label the first inner shell? Nope. 1. That's it. 1. That's our energy level. So when we go through to process this, our very first electron goes into the first energy level. On the periodic table, that would correspond to placing an electron where hydrogen is. It's that first row. Okay. The next part I want to specify is the type of orbital that that electron is located at. Okay. That type of orbital can come from looking at the periodic table as blocks, as sections. And hopefully what we notice is those first 2 columns are kind of sectioned a little bit differently from everything else. Okay. There's that giant 10 column thing in the middle that separates it from the other 6 columns. Okay, so hydrogen is located in the first column of that block. Okay, that block is commonly known as the S block. So I would call this 1S. It's in the first row, it's in that S block section. Which column is it in that S block? No, not yet, don't do that. Okay, I want to reference that there's an electron located there. So far all I've done is told you the X and Y coordinates, so I now want to specify that there's an electron there. How do I specify there's an electron? Where do I specify my electrons? In the upper right-hand corner. We're not specifying it as charge here, so we're just going to leave it as a 1. I now need to put another electron in because I've got 11 of these buggers to deal with. Where's the next electron go? Where helium is. Cool. Which row is that? It's still the first row. And now we get a little bit of a dilemma. Which type is that? S. That is going to be S. And for those people but it doesn't look like it's in that block. Hydrogen and helium are best actually drawn floated off the periodic table because of their electron configuration. They don't really fit consistently with everything else. So you will sometimes see helium written over here, and you will sometimes see hydrogen written over here. Okay. Sometimes you actually see it written in both places because they carry the, let's not worry about that. Okay. So helium, 1s, there's an electron there. Where's my third electron go? Where the lithium is. Where's the lithium? Did you just give me a sign, Jimmy? It's in the second row, right? 1, 2, 3, 4, 5, 6, 7. Which orbital type? It's in that first section. That's still an S. That was 1 electron. Where's my next electron? Where beryllium is? Good. Working on our naming there. That's awesome. What is its designation? 2s1. Second energy level, still in the S block. What's the next element? Boron. What energy level? 2, is it still in the S block? No, where is it? In the P block, so we'll call that 2p1. Where's the carbon? Where's the nitrogen? Where's the, what's next? Oxygen. Where's the fluorine? Make sure I didn't lose track of anything. Where's the neon? 2p1. Okay, we're going to take a moment here before we shift to, no, we're just going to do sodium. So where's our last electron for sodium? 3s1. We got all those ones written up there in the upper right-hand corner. Can someone do the quick math and tell me what that sum of those numbers is? That's 11. How many electrons were we supposed to account for? 11. Perfect. This works as an electron configuration. That looks really flippin' ugly, doesn't it? I wish we could condense this into some sort of fashion, like where we see repeating things. Like, for instance, you son of a horse, and you moved into my white space. I hate you so much. Technology. Try and not touch the screen. I see 1s1 repeated, right? So what could I do? Number written in the upper right-hand corner for my red. Sum those numbers for me. That's 11. That's exactly all of our electrons when we talk about sodium. This is the electron configuration for sodium. Okay? If I want to know the electron configuration for tantalum, 73, what could I go through and do? That thing in blue, I could do that all the way out 73 times. Specifying it by moving through the periodic table all the way through. We will encounter a little bit of a hiccup. Don't worry about that hiccup because I don't test on that hiccup. Okay? But there is a minor hiccup within that system. Is it really 11? That doesn't sound right. Thank you. That clock I need to fix. Okay, so that is our electron configuration. When we consider sodium, that's it. That's what sodium's electron configuration will be. On a test, you're expected to be able to identify the electron configuration for your elements. So if I tell you magnesium, you should be able to tell me the electron configuration. If I tell you phosphorus, electron configuration. Okay, you should be able to do 1 through 18. Well, let's do 1 through 20 pretty easily. 21 through 30, that's where our hiccup shows up. Most of it you're going to see tested on is that 1 through 20.
So if I was to do magnesium for the next one, could I use like the work for sodium and just kind of build off that, or it's going to be different?
I don't know. Did you do the work for sodium already? Then yes, you could use that one for sodium. Yep. Okay, because it's going to fill out the exact same all the way through. Okay. Considering electron configurations, that is a lot of work to go through and process. Are there other ways we could deal with this? Is this going to be a show your work question? Did you need to show all of that work? I would argue no. If you know how many electrons fit in the orbitals, you know how many orbital types there are, you don't need to go through all of that notation. In fact, I already saw a few people being like, why are you writing 2p1? Why don't you just tell me the number at the end? Okay, I get it. That makes a whole lot of sense. You don't have to specify them all the way out. You can go in this kind of condensed form right away. Okay, so not show your work. This is going to sit in multiple choice, which means you have to be able to discern through your multiple choice answers which of these is right. If we're out to phosphorus or silicon or even potassium and calcium, that's a lot of electrons to try and process out. What are some things that you could do to ensure you're looking at the right element? Well, we already talked through one. Sum the numbers in the upper right-hand corner. If you sum those numbers, does it hit the element that you're looking for? Yeah, that's probably pretty good. Okay. The other big part that's going to be relevant is that we really care about only a few sections of our electron configuration. I want my colors. There's my electron configuration. Which part of that electron configuration do I care about as I erase half of it? I only care about that one for this particular scenario. I care about the highest energy level. That's it. The highest energy level is my valence shell. That's directly relevant for Lewis structures. So I need to be able to quickly determine the valence shell for any individual atom. How can I do that? Take a look at sodium again. Which row is that? Third. Which block is it? S. Which column is it? So if I move to nitrogen, which row is it? Which block? Which column? So we're getting lots of different numbers there. We're talking about the columns in that block. Only in that block. Is it in the 5th column of the P block? It's in the 3rd column. That's going to be most relevant. But I cannot forget that there's things that come in front of it. What came in front of it? Well, the first energy level. How many electrons fit in the s orbital? 2. I also have the second energy level, also s block. How many electrons fit in that? 2. Which of those orbitals am I most concerned about when we talk about my valence shell? 2p and 2s. Why do I care about both? Highest energy level. The highest energy level is specified by that number in front, which means when I talk about nitrogen, I want to know nitrogen has 5 valence electrons. I want to know sodium has 1 valence electron. I want to know carbon has 4 valence electrons, and I want to know that relatively fast. Are you good at dealing with electron configurations? You think so? Cool. How many valence electrons does germanium have? Germanium is Ge, by the way. Valence electrons does germanium have? 4p2. Remember, everything in front of it is also filled, including the 4s2. So dang, you missed 4 electrons. How about sulfur? Six. You can use your electron configurations, or you can pull the valence electrons straight off the top of the periodic table. For anything in column 14, how many valence electrons do they have? 4. Rhymes with the door, which is probably where you're trying to get out to. We'll go ahead and stop there because we're 2 minutes late.